Hello, I'm James and I'm going to be discussing the solution to the first step question on assignment 20. I say the first step question because there is actually another one. The solution to that will be in a separate video recorded after this one. Okay, so what is this problem about? Well, it's all about the Fibonacci numbers. So I've written down the problem here. Hopefully you're able to read that. So it says the Fibonacci numbers, Fn, are defined by the conditions f0 equals 0, f1 equals 1, and we have what's called a recurrence relation here. So Fn plus 1 equals Fn plus Fn minus 1. Effectively what it means is that to generate the Fibonacci numbers, you add up the previous two terms in the sequence. A lot of you are probably already familiar with this sequence. Okay, so the first part of the question says, show that f2 equals 1, f3 equals 2, and f4 equals 3, and then we have to compute f5, f6, and f7. This should be a fairly straightforward exercise. It's just making sure that you understand how to use the definition of the Fibonacci numbers. Now, it does say show that, so we're going to have to be pretty explicit here. So f2, okay, so f2 by definition is f1 plus f0. F1 is 1, f0 is 0, 1 plus 0 is 1, and so we've shown that f2 is 1. Right? Simple as that. We're just going to repeat that a few more times. So f3 is f2 plus f1, f2 is 1, f1 is 1, 1 plus 1 is 2. f4 is f3 plus f2, which equals 2 plus 1, which equals 3. Okay, and that's what they've asked. Okay, I do think this level of detail is necessary because it does say show that, right? Now it just asks you to compute the next three, so you don't have to go into as much detail. I think I will though. Why not? So f5 is f4 plus f3, which is 3 plus 2, which equals 5. f6 is f5 plus f4, which equals 5 plus 3, which equals 8. And lastly, f7 is f6 plus f5, which equals 8 plus 5, which is 13. Okay? And so the next values, so f5, f6, and f7, are 5, 8, and 13. Okay? That is literally all that part of the question is asking you to do. It is really that simple. Okay. It then asks, compute Fn plus 1 times Fn minus 1 minus Fn squared for a few values of n. Guess a general formula and prove it by induction or otherwise. So what this effectively means is we're going to try and calculate the first few values. So maybe I'll write this in a table. I think that'll probably be best. So I'll have some value of n, right? And then we're going to have some corresponding value of Fn plus 1 Fn minus 1 minus Fn squared. So we'll do a few values of n, so maybe we'll see how many we need. It doesn't specify how many values of n we need to calculate this for, and so what that tells me is that basically calculate it for as many values as you need to be able to guess a general formula. So let's see. So when n equals 1, this formula becomes f2 times f0 minus f1 squared, which is simply 0 minus 1 squared, which is minus 1. Okay, so when n equals 1, this quantity is minus 1. When n equals 2, we'll have f3 times f1 minus f2 squared, which equals 2 times 1 minus 1 squared, which equals 1. It's not obvious to me what the pattern necessarily is, so I'm going to calculate it for n equals 3. So that's going to be f4 times f2 minus f3 squared, which is 3 lots of 1 minus 2 squared, which is minus 1. Okay, at this point you might be suspicious. Is it just going to be plus or minus 1? I'm going to verify this, so hopefully, if my guess is correct, when n equals 4, we should end up with a 1 here. So let's see if that's the case. So we're going to end up with f5 times f3 minus f4 squared, which will be 5 times 2 minus 3 squared, which does in fact equal 1. So I'm fairly confident in my guess that it's just going to be alternating between -1 and 1. So the sort of fancy word for guess in this sort of circumstance is conjecture. So that's what I'm going to write down. So you may see the word conjecture. You're more than welcome to use the word conjecture. It basically just means guess, and that's what we're going to try and prove. So our conjecture my conjecture for this formula is that fn plus 1 times fn minus 1 minus fn squared is going to be -1 to the power of n. Okay? You want to be careful about this power. The reason it's -1 to a power is because it's alternating between 1 and -1. The reason it's to the power of n rather than to the power of something like n plus 1 is just pick a value of n, right? When n equals 1, it's negative, and when n equals 2, it's positive, right? And so that implies that we need just n here, right? Because when n equals 2, we'd end up with -1 squared, and that would be positive. Okay, so it's to the power, so it's -1 to the power of n. Okay, let's go back and see what the question said. It said, guess a general formula, which we've done, and prove it by induction or otherwise. Now, when a question says, basically tells you how to prove it, right? It says, prove it by induction or otherwise. 95% of the time, you're going to want to do it the way they say, okay? So that's what I'm going to do. I'm going to prove it by induction. I'm not even sure what an otherwise method would be. I guess if you knew the general formula for the Fibonacci numbers, you could probably use that. Maybe there's some clever trick you could use, but like I said, 95% of the time, I mean almost 100% of the time to be honest, it's going to be better for you to do it the way they say. Okay, so we're going to prove it by induction. So I'll tell you how I lay out an induction problem like this. It's a fairly good, rigorous layout. You may have been taught it slightly differently. As long as it's clear what you're doing, any approach should be fine. The way I tend to do it is I'll say, let P of n be the proposition that we're sort of wanting to prove here. So in this case, the proposition is fn plus 1 times fn minus 1 minus fn squared is -1 to the power of n for n greater than or equal to 1. That's our proposition. Recall, for a proof by induction, you're going to have to prove a base case here. So in particular, we're going to prove it for n equals 1. So on the left-hand side, we end up with, let's see, we're going to end up with f2 times f0 minus f1 squared, which equals -1, and that is clearly -1 to the power of 1, which is equal to the right-hand side. Okay, so clearly the statement is true for n equals 1, so our base case is proved. So maybe I should just say, so P of 1 is true. Okay, and now we have to make an assumption, so we assume that P of k is true. So we're assuming it's true for some arbitrary n equals k. So assume P of k is true, so what does this mean? It means that fk plus 1 times fk minus 1 minus fk squared is -1 to the power of k. And our aim, what we're sort of wanting to prove here, is that P of k plus 1 is true. So our aim is that fk plus 2 times fk minus fk plus 1 squared is -1 to the k plus 1. Right? That's what I'm aiming to prove. Okay. So, how would I want to do this? Well, what do we know? We know that this is true by assumption, right? We've assumed that this statement is true. But we've also got a relationship right at the very beginning of the question for the Fibonacci numbers, right? So we do also know that fk plus 1 equals fk plus fk minus 1. Okay, and hopefully we can use this assumption and this fact to prove our aim. Okay, that's basically what the goal is going to be here. Okay, cool. So, we're going to rearrange this statement. So this is equivalent to saying, so this arrow, this symbol here just means is equivalent to. This is equivalent to saying that fk minus 1 equals fk plus 1 minus fk. Now you might be wondering, why am I using this formula? Well, it's because I know that this is true, and I know that this is what I'm aiming for, and I realise that what I know has got this weird fk minus 1 term in it, and what I want to prove doesn't have the fk minus 1 term in it, right? And so it makes sense to me to try and substitute in this fk minus 1 term just to get rid of it. Okay, so that's what we're going to do. We're going to substitute in this term into this expression here. Okay, so what does that give us? Well, that gives us the fk plus 1, so we're not going to write fk minus 1 anymore, we're going to write this expansion here, this fk plus 1 minus fk, minus fk squared equals minus 1 to the power of k. Simply expanding the brackets, we end up with fk plus 1 squared minus fk times fk plus 1 minus fk squared equals minus 1 to the power of k. Now, it makes sense to me, right? We're trying to get a minus 1 to the power of k plus 1 term. We've only got a minus 1 to the power of k term, so it makes sense to me to multiply through this entire expression by minus 1. Okay, so what does that give us? That gives us that fk squared plus fk times fk plus 1 minus fk plus 1 squared equals minus 1 to the power of k plus 1. Again, simply just by multiplying our expression by minus 1. And I'll just write a logical equivalence here, right, because that's what we're doing. We're going from this step to this step. Okay. And now we're just going to simply do some clever factorizing. So I can factor out a factor of fk from this term, right? Because if you realise, like, what we've got is almost what we want, right? Like, we've got this minus 1 to the k plus 1, we've got this minus fk plus 1 squared term. We just need to get this fk into fk times fk plus 2. So I'm going to factor out fk, and we'll be left with an fk plus fk plus 1 minus fk plus 1 squared equals minus 1 to the k plus 1. But by definition of Fibonacci numbers, fk plus 1 equals fk plus 2. So this can be written as fk plus 2 times fk minus fk plus 1 squared equals minus 1 to the k plus 1. And so we can say that p of k plus 1 is true. It might be worth writing a quick conclusion. So the conclusion I usually write for an induction is, I would say, since p of 1 is true, right, that was our base case, and if p of k is true, then p of k plus 1 is true, which is what this statement says, by the principle of mathematical induction, p of n is true for all natural numbers n greater than or equal to 1. Okay? Do you need to write a conclusion as detailed as that in the exam? Honestly, probably not. But just to be thorough, that's one way to write a conclusion. And that's what the question asked, right? The question asked, guess a general formula and prove it by induction or otherwise. We have actually done that. Okay. The next part of the question says, by induction on k or otherwise, show that this statement is true for all positive integers n and k. Okay, so I'm going to move over to the other side. So, as before, actually it might be worth mentioning here that it tells you what to do induction on, right? So last time, for our formula, we did induction on n, okay? They're asking us to do induction on k, okay? Now this is completely fine, you can do induction on any variable you want. You've just got to be very careful here not to get sort of mixed up with our expressions and stuff, right? So for example, at the start of the proof I said let p of n be the proposition. That's because I was doing induction on n. Now we're doing induction on k, I'm going to have to start by saying let P of k be the proposition. Okay, so that's what I'm going to do. So let P of k be the proposition that fn plus k equals fk times fn plus 1 plus fk minus 1 fn, and this is true for all n and k which are positive integers. Okay, if you haven't seen this notation before, this basically just means, so fancy z plus basically just means positive integers, and this little e here means as an element of, because this is a set. Okay, so this is a fancy way of saying n and k are positive integers. Okay, so yeah, that was the statement. This is what I want to prove. Okay, that's what the question asked. Okay, so as before, we're going to do a base case. Base case. So we're going to do P of 1. And so what are we going to do here? So the left-hand side is simply equal to f of n plus 1. The right-hand side is equal to f1 times fn plus 1 plus f0 times fn. F0 is 0, so f1 is 1, so this just simplifies to fn plus 1, and this equals what we found earlier, the left-hand side, and so P of 1 is true. Okay, so that's the base case proved. So what I'm going to do is, okay, here's some knowledge that, because I've already done this question, I know what I need to do here. It turns out that we're actually going to have to use a second assumption. Okay, so what I can do from this is I can assume the statement is true for P of n minus 1. Okay, so we can assume that P of n minus 1 is true. So what that means is that f of n plus n minus 1 equals f n minus 1 f n plus 1 plus f of n minus 2 fn. Okay, I can make that assumption. And I'm also going to need the fact that P of m is true. Okay, I'm going to have to use both assumptions. Okay, and you'll see why I need both of them in a second. But when you need to make two assumptions, you actually need to prove two base cases. Okay, so we're also going to have to prove P of 2. Okay, so for P of 2, the left-hand side just equals f of n plus 2, and the right-hand side equals f of 2, f of n plus 1, plus f of 1, f of n. Just substituting in the numbers, this is the same as f of n plus 1 plus f of n, which by definition of the Fibonacci numbers is f of n plus 2, which is equal to our left-hand side, and so P of 2 is true. Okay. Now, if you're a little bit confused as to why I've had to prove P of 1 and P of 2, so what this allows me to do is I can now assume that P of m is true. Okay, so what that means is that f of n plus m equals f of m, f of n plus 1, plus f of m minus 1 times f of n. Okay. Yeah, so if you were confused why I had to prove both P of 1 and P of 2, and why I needed both of these assumptions, you will see why in a second. Okay, and I'll talk about that a little bit later. Also, as a quick side note, notice that I've said things like assume P of m is true. I have not done what I've done last time and said assume P of k is true, because in this case, k is actually what we're inducting on, right? And so you need to be very careful about what letters you use. Okay, so make sure you know what you're doing here. Okay, I can't say assume P of k is true, because P of k is actually what our proposition is. Okay, so we have to use some other letter. I've used m, but you could use anything you like other than k and n. Okay, so what's our aim? So our aim at the end of the day is to prove P of n plus 1, right? So that would mean f of n plus m plus 1 equals f of m plus 1 f n plus 1 plus fm times fn. Okay, so that's what we want to prove. Well, what do we know about fn plus m plus 1? Well, by definition, it's equal to fn plus m plus fn plus m minus 1, right? Now, imagine that we had only done one base case and assumed that only p of m was true, or something, right? Then we would only have this expression, and we wouldn't actually have an expression for this thing here. That's why we needed to do two base cases here to make these two assumptions, because I need expressions for this thing and this thing, okay? So that's why I need to do that. Now, obviously, like I said, I'd read the question, I'd done the question beforehand, and so I knew that I needed to do this. In the actual exam, and what I did when I first did this question, is I got to this point, I'd only done one base case, and I realised, oh wait, I need to use two things here, and then I went back and did the second base case, okay? And so that's totally fine. Like, if you only did one base case and realised, oh, I should have done another one, that's totally fine. Just write here something like, oh, I need to use a second assumption, so I will prove a second base case, or something like that. Okay, that's totally fine to do. I just did it beforehand just to make the solution look a bit nicer. Okay, so now we have an expression for fn plus m and fn plus m minus 1 by our two assumptions here, and so we're just going to substitute those in. So fn plus m is fm fn plus 1 plus fn minus 1 fn, and this fn plus 1 minus 1 here is fn minus 1 fn plus 1 plus fn minus 2 times fn, right? We're going to do some factorization here, so in particular I'm going to factor out the n plus 1 term from these two. The reason I'm doing that is because I know in our aim I want an n plus 1 term, so I might as well gather those together now. So this becomes fm plus fm minus 1 times fn plus 1, right? And we also want an fn term. Well, let's group those together. That would be an fm minus 1 plus fm minus 2 times fn. By the definition of the Fibonacci numbers, fm plus fm minus 1 is fm plus 1. That's fm plus 1. Plus this thing here is fm, and this is fn, and that's exactly what we wanted to prove. So p of m plus 1 is true. Okay, and so we're going to do a conclusion again. So how would I write the conclusion this time? I would say, since p of 1 is true and p of 2 is true, and now this is some fancy notation. Again, I think it's a little bit overkill, but I think it's nice and concise, and it states the following. So if p of m minus 1 and p of m is true, then p of m plus 1 is true. Okay, let me just explain this notation. So remember last time, all I had to write was if p of k is true, then p of k plus 1 is true. That's not enough in this case because we actually made two assumptions, and so we had to say that if p of m minus 1 is true and p of m is true, so this little hat symbol here just means and, okay, in logical notation. So if p of m minus 1 is true and p of m is true, then p of m plus 1 is true. That's what that says. So by induction, p of n is true. Okay, I didn't write out the whole thing again, right? You could easily say, by the principle of mathematical induction, p of n is true for all natural numbers n greater than or equal to 1 or something like that. Oh, hold on. That should be k. P of k is true. That's what we were actually proving, wasn't it? Yes. Okay, so I could have written out in full, but I think honestly this is enough. Just say by induction, that's true in your conclusion. Okay, that was the whole question. sort of reflecting on what this question was like, honestly, it's just, it sort of guides you through it, right? Like, here you just calculate some Fibonacci numbers, make a conjecture, and then it's just using induction twice, okay? The main trick in this question is knowing that if you need two base cases, you need to make two assumptions. Or, hold on, maybe I said that the wrong way around. If you want to make two assumptions, you need to use two base cases. That's what I meant. Yeah. Okay. So yeah, that's the whole question. Fibonacci questions and sort of induction, I would like to say is a fairly common thing on the exams. It's definitely appeared a few times. So maybe if you want some more practice with this, just type up Fibonacci into the STEP database, see what comes up. If I'm not mistaken, there is another Fibonacci question on the assignments. I will also be looking at that. So yeah, okay. Hopefully you've understood this and that my writing is clear enough, and I'll see you for the next one. Thanks.